Hello, y'all. Welcome to lesson 129 of my DP chemistry curriculum. Today we're going over reactivity 3.4.9 and 10. These are HL topics. In 3.4.9, we're going to talk about nucleophilic substitution reactions, which include the reactions between halogenoalkanes and nucleophiles. Furthermore, we're going to describe and explain the mechanisms of the reactions of primary and tertiary halogenoalkanes with nucleophiles. Within this, we'll distinguish between the concerted one-step SN2 reaction and the two-step SN1 reaction. Then we'll finish this with a very short discussion on the rate of substitution based on the identity of the leaving group. This is going to be overall quite a long video, but there are a lot of things to go through that all kind of work together to form one topic. So with that said, let's jump right in with what we already know because we looked at substitution with nucleophiles. So we have, oh, a little bit too big of a writing utensil. So we already have substitution with nucleophilic reactions with halogenoalkanes. We've seen an OH minus displace some leaving group X that's bonded to something. And when we see this reaction, this is usually our halogen, and it is called our leaving group. But what we haven't talked about is this actually can happen in two different reaction mechanisms. And it changes based on the halogenoalkane. Changes based on reactant. So let's look at two different reactions here. We could have the halogenoalkane R something, and we'll throw some carbons, and that is attached to some leaving group X plus a hydroxide. And we know that that hydroxide is a nucleophile with those two electrons, which will attack the carbon, and we get this sort of reaction mechanism. This is what we've already explored to create this primary alcohol. So, plus our leaving group. Cannot forget the leaving group. Now, that is a very simple reaction mechanism, but what if we have a different what if we have a different electrophile or a different halogenoalkane, maybe something that looks like this? Plus OH. We still know that this is going to be the overall reaction mechanism, but there's something different here. In this case, we have a tertiary alcohol as our product, as we're starting with a tertiary halogenoalkane. And the thing about this is both of these have completely different elementary steps. And we learn that those elementary steps are those intermediate steps or the smallest steps of a reaction, these basic steps of reaction. They can be unimolecular, bimolecular, and in rare cases, termolecular, but they differ between these two types of reactions. And there's a lot of reasons for it too that we'll go through this. But the main thing that happens here is two things actually must happen. Two things must happen in both reactions. Now, one of the things, and I'm not going to say first because it changes, is that we must have the bond between carbon and the leaving group must break. So we have to break that bond somehow to get the leaving group to depart. We also have a nucleophilic attack on the partially positive carbon. So both of these happen. But the real question is, which happens first? And why? So you'll notice in both of these reactions, that bond must break, giving the electrons to the more electronegative leaving group. And we also have that attack of the nucleophile on the carbon. But why are they different? And how does one going first affect the other? So we're going to explore this in this unit. The main points here are that the structure of the carbon, primary versus tertiary, and secondary, but we're not going to discuss that in this unit, plays the main role of being, and I'm going to introduce two new terms, an SN1 reaction or SN2. And so we're going to go over what this means. S sub n just stands for substitution, nucleophilic, as that's the kind of reaction that's taking place. It's a nucleophilic substitution reaction. But the 1 and the 2 stand for either unimolecular or bimolecular as the reactants in the elementary step. So we're going to look at those elementary steps as we describe the reactions. Now, we're going to start off with SN2 reactions. So remember, that's going to be a bimolecular step. So within SN2 reactions, this is a reaction mechanism where substitution and breaking of the carbon leaving group bond occur simultaneously. So instead of one of those happening first, they actually happen at the same time. This is, we're going to actually look at it as if it's two separate things as we describe the reaction mechanism. And you may even have to describe it in your DP exam as two separate things. But it's important to note that this is actually a simultaneous occurrence. So the important thing here, and I'm not going to use therefore actually, the important thing here is that this proceeds in one step and only with primary halogenoalkanes. And so we're going to figure out why it only happens in primary halogenoalkanes. And really, it's due to, oh, I'm going to change the color of this. This is due to what we call steric hindrance. I don't think there's an E in the middle of hindrance. So it's due to steric hindrance. Now, if we're going to break that word up, steric comes from the same root as stereoisomer. So we're talking about specifically the space around the carbon. Carbon being obstructed. So if there's steric hindrance, then around that carbon that's bonded to the leaving group, it's obstructed. Now, in primary halogenoalkanes, there is no steric hindrance. And we can see why. If we look at a primary halogenoalkane, we have a carbon bonded to a leaving group, bonded to one at maximum R group with two hydrogens. Now, if we use a stereochemical formula as well, and I'll go ahead and draw that with a stereochemical formula. Oops. R X H H. The hydrogens are really small. And because the hydrogen is small, it kind of leaves space for nucleophilic attack. You can see kind of like this glaring open space right here in the back of carbon where there's nothing really getting in the way closer to the hydrogens. And it's just open for this to be attacked by a nucleophile. So there is what we call no steric hindrance. So let's go ahead and look at the actual reaction or an example of an actual reaction. So in this example, we're going to look at chloroethane, CH3, CH2, Cl. We don't have to name where the chlorine is because it's ethane, plus a hydroxide. Now that hydroxide, this being a substitution mechanism, is going to replace it to make ethanol. And we're going to get CH3, CH2OH plus Cl minus. That's the reaction that we know is going to happen. But what does this actually look at? I'm going to be using our stereochemical formulas here so that we can see in space where this is occurring. Oops. We have named this chlorine. So we have our chlorine bonded, and then we have our hydrogen and our hydrogen. And so, like I said, there's that open space in the back where OH can go ahead and attack. Now, a couple things to note here is that we know that OH won't come around the chlorine because it's very electron rich. The chlorine's very electron rich. They kind of repel each other, so they don't want to attack there. However, in this, we do know that the carbon is partially positive because of that electronegativity difference. And because of that, it is an electrophile, and the nucleophile is going to attack it. So this is going to be that initial step slash the only step in this reaction. What happens, and this is the part that the DP exam likes you to kind of be able to demonstrate, is we actually get this transition state. Now I'm going to use my words very carefully. This is not an intermediate. I repeat, this is not an intermediate. This is not stable. It doesn't really exist because as that OH comes into bond, what it's immediately going to do is kick off that chlorine. But it's important to note that this transition state is something that kind of occurs so that we can see this happen. Once again, it's not an intermediate. It is not a stable form. It does not exist in solution. We cannot isolate it. Remember, that's the thing about transition states. They cannot be isolated in reaction. And so what we end up happening is we end up getting this new chemical, our ethanol, and we get this new stereochemical formula here, plus our chloride ion. So as we saw in that intro that I did, this is what we call a one-step, one-step concerted reaction, meaning that we have absolutely no intermediates, nothing to isolate. And what we know is happening is that we have that nucleophile is attracted to carbon to form the unstable transition state. Then the leaving group being more electronegative, the more electronegative, I think I've been using capital EN for that, electronegative leaving group, and being, by the way, I'm saying more electronegative in relation to carbon, uh, pulls electrons to itself. So, like we said, while this is not an intermediate, um, this is the reaction that occurs. Now, a couple things to note. We actually call this reaction a backside attack. Oops, I want to make a star. This is referred to as backside attack. And you can see why, because it comes on the backside or the opposite end of the leaving group. Nucleophile attacks opposite end of leaving group. Because once again, those leaving groups and the nucleophile are both electron-rich species repelling each other. This is pretty much always what we call, this is what we pretty much always refer to SN2 reactions as. Furthermore, this inverts the configuration. Because once we had a tetrahedral, and I'm going to try and use colors to kind of represent these, and I'll use blue as the leaving group, or as the nucleophile. And what I'm going to do is kind of explore this with our, is just assuming hydrogens only. You notice that originally we have this kind of tetrahedral shape, and I should actually use our stereochemical formulas. And when this comes in and attacks it, the whole tetrahedral flips. And so we get this new shape where we have still our central carbon, our leaving group off to the side, but now the hydrogens are kind of flipped a little bit, and they kind of are pushed back by that new bond. So the entire tetrahedral is going to invert itself. Oops. And this is where we can look at our molecular geometry to help us out here, because that is going to create that repulsive force. The new nucleophile is repelling those hydrogens, pushing them away, creating this new molecular geometry. It always occurs like this. Always, always, always occurs like this. And because inverse configuration occurs like this is what we call stereospecific, meaning only one isomer. And because we're talking about carbons and those isomers, we're specifically talking about those optical isomers or chirality around the central carbon. It's always going to be that way. Furthermore, because we must have both reactants here, the rate of reaction is dependent on both nucleophile and halogenoalkane concentration. You know it's bimolecular because our two reactants all the way up here are our halogenoalkane and our nucleophile. This elementary step, being the only step in this one-step reaction, has two reactants. It's bimolecular, which we know because we called it an SN2 reaction. And it's really dependent on how those two collide. If we even look at those two steps going back up here, this step occurring is that rate determining step. This actually is what we would refer to as the slow step if we were to look at it too, while this is fast. So while it's one step, that initial step is the rate. It is very slow for these two to collide, but if we increase the concentration, it still increases the rate of both. The last thing for SN2 is if we were to make our rate equation based off what we know here, we know that rate is going to be equal to K, and because it's dependent on both, we can say the concentration of the nucleophile times the concentration of the halogenoalkane. And looking at this rate equation, we can determine that it is second order. We know that because we have a 1 and a 1 coefficient, so it's first order in reference to each specific reactant, but overall the reaction is second order. And if we were to look at an energy profile, the DP loves to give you energy profiles and have you determine whether this is SN2 or SN1. And progress. Because this occurs in one step, we can just assume what we would see as a standard energy profile. We have our reactant, we have our transition state, and having the highest energy, you can really see how unstable it is, and then we have our product. And so basically, this whole reaction depends on whether or not those two reactants can collide, make that bond, which forms that transition state for a moment as we get to our product, something that can't be isolated, being the transition state, with the product being the final thing, and it also being stereospecific. So that's everything about SN2 reactions. With that said, let's move on to SN1 reactions. They have a bit more of a complex reaction mechanism, but now doing the SN2, it's a bit easier to figure this out. Now, this occurs in tertiary halogenoalkanes. Now, the reason this only occurs in tertiary halogenoalkanes is these have steric hindrance. So while primaries did not have steric hindrance, which is what allows for that backside attack, these do have quite a bit of steric hindrance. When we look at our tertiary halogenoalkane, we have our carbon and our halogenoalkane, but we've got some big R group, some big R group, and some big R group. And these are honestly quite large. They take up a lot of space. And because these are large and take up a lot of space, really, what we're saying is that there is no room on carbon for nucleophile or nucleophilic attack. It will probably be repelled or blocked by those R groups. So we first must remove the leaving group. So that's how we make space on the carbon. We just get rid of the leaving group. This will end up, this will end up forming a carbocation. We talked about these when we talked about different types of nucleophiles and electrophiles. A carbocation is a very powerful electrophile, and that's because it has a full positive charge over the entire hydrocarbon. So let's look at that first step. We'll do something like methylpropane or uh, 2-chloromethylpropane. So we have our carbon, our CH3, 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 and our chlorine. With those, like we said, there's no room for that attack, and this is our first elementary step. What we have to wait for is just for, at some point, this bond to break and give its electrons to chlorine. This literally is something that you just have to wait to happen or provide enough energy into the system for this to happen, because once again, chlorine is far more electronegative. Because this is that step where we're just waiting for it to happen or waiting for a bond to just break, this is actually very slow. We have to add a lot of heat or some type of situation to make this happen faster, but this would be our rate determining step. And as our rate determining step, you can see that this is where we get the term SN1. There's only one reactant. Rate determining. And we'll put our chlorine or chloride ion there. Therefore, this is unimolecular. So again, that's where we get SN1. So now that we have this carbocation, we are now open to nucleophilic attack. Something I want to point out before we take a step further is this is specifically an intermediate. This is stable. And if we look at the carbocation, which I'm going to simplify just using R groups, it has 3 bonds, meaning that this is trigonoplanar. And because it's trigonoplanar, it's actually open to nucleophilic attack on both sides of this plane. So the nucleophilic attack can come from the front or the back. If we're thinking about a triangle in space or a plane in space, it has 2 sides to that plane, and those are equally open to attack. We're going to come back to that when we talk about isomerism with our products. But we can then do our nucleophilic attack, which will look something like this. CH3, I'm going to take the same product as before, CH3, CH3 plus. And again, that's our product from up above. And we'll use OH, the same nucleophile we used before. And of course, it will attack the carbon. This is a very fast reaction. It's 2 ions coming together. They like to do that. Electronegativity and electrostatic interactions tell us that oppositely charged ions will attract and form a bond. And so we get methylpropane 2-ol. And I'm not actually going to worry about our stereochemical formulas for this one, and we'll discuss why as a continuation to what I mentioned about the molecular geometry being open to attack on the front or back. But the key thing here is that the 3 alkyl groups stabilize the positive charge, specifically the carbocation. The charge is shared across the three bonds. And that allows the carbocation to be stable, or specifically what I said before, which allows for stable intermediate. Now, because of that, and because we can see that the concentration of tertiary halogenoalkane is the only reactant that rate depends on, therefore we call it SN1, referring to the unimolecularity. All right, so because we know that we form a stable intermediate, the energy profile for an SN1 reaction looks very different than for an SN2 reaction. And again, the DP loves, loves, loves to give you these types of uh, energy profiles and have you tell them whether it's SN1 or SN2 and how do you know. And so we have our reactant, we have our products, and we actually have this other stable dip. This is our intermediate carbocation, carbocation. Furthermore, we can recognize what's happening at each of these peaks. That first peak, that one that has the highest activation energy, and we know that because it's also the slowest part of the reaction. So we can guess that that's the first step. This is the leaving group departure. Then the second thing that has to happen is that other peak. This is our nucleophilic attack. You'll notice it has a much smaller activation energy, being a much faster step overall. So another quick thing I want to note is that carbocation is much less stable than our reactants. That's kind of what also makes it so slow. And so we're going to have that at a higher energy than our reactants. All right. So I said I'm going to come back to isomerism, and because of that kind of attack from either side, the carbocation can be equally attacked from front or back. Because it's an equal percentage, 50-50, we therefore make a racemic mixture of isomers, which when we say racemic mixture, we already know it's a 50-50 of those optical isomers. And therefore, this will always be half-half of whichever optical isomer if you have a central chiral carbon or a chiral center. So that is all 3.4.9. We finished that section. Like I said, we'll move on to 3.4.10, which is much shorter, which is just how does the leaving group affect rate? Now, leaving group affects rate in both of these, but a little bit more in one than the other, and we can see that in just a moment. But they can increase or decrease based on leaving group. And that's because we have to look at the heterolytic fission of the carbon X bond. So if this bond is weak, then that equals a faster reaction. because we can break that bond more easily, specifically in those SN1 reactions where we have to break that bond before we can even proceed. So how do we figure out whether the bond is weak or strong? Well, that's quite simply electrostatic interactions between our halogen and carbon. So as we move down halogen group, a couple things happen. First, the halogens get bigger. And because those halogens are getting bigger, therefore two things happen. Therefore, the uh, bond is, or bond length is larger. We also have electronegativity decreases. And overall, I'm going to say overall, bond is weaker. So as we move down, we get a weaker bond, meaning we'll have a faster reaction. And specifically, we're going to have those differences in polarity, and we're going to have those larger halogens. So it's just going to make this whole reaction faster overall as you move down towards like iodine as your leaving group. Well, iodine's a very good leaving group. It leaves very readily because it's very large with an electronegativity close to carbon, very large bond length. This is easy to break. So I hope this helps you understand a little bit about SN1 and SN2 reactions, and have a great